Ladies and gentlemen, the last lecture of Unit 2. Here we go. The normal approximation to the binomial distribution. Yes, I'm going to say it right here. Every single question on this entire worksheet is a binomial distribution question. However, we're going to be answering some of these questions with a normal distribution, with a normal curve. It's almost as if there's going to be a marriage today between the normal distribution and the binomial distribution. Holy corniness. Oh my goodness. All right, enough of that. Okay, so anyway, moving right along. Let's read number 1 here. If we have a binomial experiment where n equals 8 and p equals 1/2, list the binomial probability distribution and the corresponding probability histogram. All right, first and foremost, I see that p equals 1/2. And whenever I see that, I see the super duper shortcut. So it's time right now to take this video and pause it and find your Pascal's triangle. Find Pascal's triangle right now. And once you find Pascal's triangle, start this video up all over again. I'll give you a second here to pause. Okay, there's my 1 second. All right, so because there are 8 trials, because n equals 8, I happen to have this prepared already. My random variables go through from 0 successes through 8 successes. If you go down to row 8 of Pascal's triangle, you see the numbers across row 8, and then on the far right you see 256. That's not only the sum of the numbers in that row, that's the denominator of the probability. So starting right here, probability of 0 successes would be 1 over 256, and then 8 over 256, and then 28 over 256. Again, I'm getting these from row 8 of Pascal's triangle, 56 over 256, and then 70 over 256, and then symmetrically back down, 56 over 256, 28 over 256, 8 over 256, and 1 over 256. So for brevity, I happen to have the histogram already drawn and labeled. What a great teacher I am, my goodness. So then I made my y-axis go all the way up to 70 out of 256, and I went by tens. So now I'm going to create my histogram. The first bar just goes up to 1. I know that's not perfect. The next one goes up to 8, then up to 28, then to 56, then up to 70, then symmetrically back down. And what I get is a nice, actually bell-shaped histogram. Would you agree? I would too. All right, that's number 1 done. By the way, on test number 2, I'm going to ask one question where I ask you to make a probability distribution. Probability distribution in general is just this right here. If I ask you to make a probability distribution, that's what I'm asking for. How you find the probabilities is a matter of the question itself. If things are binomial, you could use the calculator or the back of your book, or if p is 1/2, you can use Pascal's triangle, the super duper shortcut. All right, if it's not binomial, you can make a tree diagram. There are many ways of finding those probabilities, which we've talked about through this course. All right, so let's get to example 2, because I'm realizing that I might only have 10 minutes to make a video. I think beyond that, YouTube says it's too big. So let's get cracking. From example 1, find the probability of getting between 3 and 5 successes inclusive. All right, so it says use the binomial formula or the calculator program. To be honest, I'll use the calculator program, but I want to use this first. 3 and 5 successes. Let's use our probability distribution. Isn't this just the probability of between 3 and 5 successes? Let me just take those 3 fractions. Let's take 56 out of 256 plus 70 over 256 plus 56 over 256. And if I add those up, I get 0.71099375. Or, as a fraction, it's 91 over 128. Where I got these answers, you might be curious. Well, I actually used my calculator program, and I want you all to think of which program should get used here. We're finding 3 separate binomial probabilities and adding them up. So it is actually the BinoSum program. Take out your calculators, pause the video again, take out your calculators, use the BinoSum program. The probability is 0.5. the trials, is 8. The high successes, it says between 3 and 5 inclusive, so the high successes would be 5. The low successes would be 3. Plug all that in the binosum and confirm that you get this answer right here. This right here, keep in mind, is the exact answer. It is the exact binomial answer. So we got the exact answer, and we got it in a matter of seconds. So now what is up with this normal approximation? Well, normal approximation means normal curve. But what two pieces of information do we always need to answer any normal curve question? We need to know the mean. Let me write it over here. The mean and the standard deviation. But wait, this is a binomial question. How do you find the mean and standard deviation of a binomial example? The mu is n times p. It's the shortcut we learned about the other lecture, and the square root of npq. So n times p is 8 times a half, which is 4. And standard deviation is the square root of 8 times 1/2 times 1/2. So half of 8 is 4, half of 4 is 2, the square root of 2 is 1.414. Remember to round your standard deviations to 3 decimal places each. Okay, so I'm going to put 4 right in the middle of this curve. And I need to find the probability between 3 and 5 successes. There's one huge issue here, and this is the main part of this lesson, something you have to get down. Okay, look back up at the histogram. Notice that the third rectangle doesn't begin at 3. It begins right here. This is an important point. Notice that the fifth rectangle doesn't end at 5. It ends right here in between 5 and 6. The third rectangle actually begins at 2.5. And the fifth rectangle actually ends not at 5, but at 5.5. This concept right here of not starting at the number, but starting 0.5 away from the number has an actual name. It's called the continuity correction factor. Whenever you approximate a binomial distribution with a normal curve, you must do this continuity correction factor, or CCF as we say it in the industry. I'm lying. There is no industry and there's no saying like that. I actually just call it a 0.5 adjustment. In layman's terms, I just call it a 0.5 adjustment. Whenever using the normal curve to answer a binomial question, you do a 0.5 adjustment on the number. So what I do is, instead of starting at 3, I imagine there's a little histogram around the 3, and I imagine there's a little histogram around the 5. I'm sorry, a rectangle, not a histogram. Instead of starting at 3, I start 0.5 units away from the 3. In order to include this third rectangle, I need to begin at 2.5. And then I shade to the right. And I want to include the entire fifth rectangle, so I must end at 5.5. So I'm actually not, I'm going to cross off 3 and 5 because I don't even want to view those numbers. From this point on, this is just a z-score question. Let me scroll back up. These are the raw scores, and I'm going to convert them into z-scores. Okay, so in order to do that, I need to use my z-score formula. Let's get to it. All right, the z-score of the mean is always 0. The z-score of 5.5, that's going to be 5.5 minus 4 divided by the standard deviation, which is the 1.414. And once I do that, I get a z-score of 1.06. That z-score goes right here. If you take a look, 2.5 is the same distance from 4 as 5.5. I could do the z-score for 2.5, but if you follow me, this z-score is just going to be negative 1.06. Capiche? All right, because if I put a 2.5 here, I'm going to get negative 1.06. If I look up 1.06 on my z table, I get 0.3554, and I get 0.3554 here. Add them together, and I get 0.7108. And that is my approximate answer. So now I know what you're all asking here. Mr. Clody, if I can get the exact answer in a matter of seconds, why would I do all this work to get an answer that's just an approximation? That's a great question, which I'm going to answer in part 2 of this video, which will begin after I stop this video.